Good morning, everyone. Sorry, I had some little technical difficulties over here. My name is Alexey Andreev. I work in Facebook Data Center Network Engineering. And I'm going to talk about F16, our next generation data center fabric. Yesterday, we introduced the F16 along with the building blocks for it. Today, in this session, I'm going to focus on the networking aspects of this new network design. Let's start with an overview of our classic Facebook fabric. This network has been running in production for us for several years. It's been a reliable workhorse for us. We have dozens of instances successfully running. The main building blocks of the fabric are server pods. They aggregate rack switches. Each pod has 48 racks in it. They connect to 4 parallel spine planes, which facilitate the communications between the pods. They contain spine switches. There is up to 48 spine switches per plane. The fabric switches essentially connect the pods to spines. It's a multi-tier topology. There are special pods, which we call edge pods. They connect to spine in the same exact fashion as the server pods do. But instead of racks, they contain uplinks to other fabrics in the region, to our other data center regions, and outside vault. The fabric can be completely non-blocking. It's designed for this. What this means that for every 48 server rack downlinks in the pod, we have 48 uplinks on the fabric switch to the spines. Practical so far has been 2-to-1 subscription ratio, not full 1-to-1 yet. All the links in the fabric are 100 gig. We started our fabrics with 40 gig back in 2014, but since then we upgraded. The fiber is single mode, and the routing in this network is all BGP, from the top of rack switch to the exit from the fabric. It's all BGP-based routing. Let's take a closer look on the server pod. As I mentioned, server pod contains 48 rack switches. And in our case, this is our in-house platform. It's Wedge 100S. The 4 fabric switches aggregate these rack switches of the pod. They can be backpack, but our pods are compatible with OEM switches as well. Each rack has 4 100 gig uplinks to each of the fabric switches. So essentially, this gives 400 gig connectivity per rack. The fabric switches, we call them FSWs, facilitate communication from the pod to all other pods in the fabric. This is pretty much the way for the pod to go out. They also facilitate the intra-pod communication between the racks. Looking on the spine planes, the parallel spine design gives us multiple benefits. One of them is scalability. With reduced partial meshing connectivity, we're able to build bigger networks without bigger switches. They also give us capacity. The load is balanced between the planes and within the planes, utilizing all of the spines available in the spine tier. They give us reliability. The spines are pretty well-contained failure domains. They actually don't even know about each other's existence. They're completely independent, which allows us to improve reliability of network, and which helps us during large-scale operations. For example, for introduction of F16, we had to completely redo the routing design inside the fabrics, and having the plane structure helped us to do this on the fly, smoothly, and completely transparently. The other advantage of parallel design is flexibility. The planes are independent, and they can be based on different technologies inside. They don't have to be even the same routing technology. Our fabrics are not standalone entities. In our typical data center locations, we have multiple buildings with fabrics connecting together through yet another tier, which is essentially a fabric of fabrics. We call it fabric aggregation, or FA. Our original design was sized for up to 3 large buildings, or 3 large fabrics. And each fabric could grow to hundreds of terabits of uplink capacity to this regional network at the maximum build footprint. This network was a reliable workhorse for us for several years. But over time, the new capacity pressures started appearing. From one end, from the top of the network, we would like to make our regions bigger. We would like to go beyond 3 buildings. But each additional buildings in the fabric means increased east-west traffic from fabric to fabric. From the bottom of the network, the growing disaggregation is putting another pressure on the racks. The applications like disaggregated storage, artificial intelligence, video services start requiring near terabit capacity per rack. Both of these pressures also require larger spine capacity on our fabric. We needed an increase of 2 to 4x. When designing data center network, we look on many parameters. It's not a standalone system. It's highly interdependent. On one hand, we have classic network variables, speeds and feeds, scalability, topology, routing protocols, routing designs. Regional composition, we need to be aware of other fabrics in the region for interoperability and compatibility. Life cycle, for us the fabric and the networking is not only about building new data centers. We have a large fleet of existing data centers, and upgrading the existing network to the same new standard is the same important for us as building new networks. And network automation and management. On the other hand, there are parameters that are not necessarily directly in the networking domain, such as what are the servers and services? What switch ASICs are available? What are their parameters? What are other hardware components involved? Optics and link speeds, power and cooling, fiber infrastructure, physical space, and more. Underneath it all, there are timelines. When do we need the new network by versus when the technology is available, how long it takes to develop. And in case of our F16 design, our need by was 2019, deployed early 2019. The main considerations that influence the design are optics and link speeds, as well as power and cooling. And the main network goals were bandwidth capacity and scalability. Let's talk about the constraints a little bit. One of them is optics. One way to achieve our desired 4x increase of the capacity would have been to go to 400 gig links in the fabric. However, we have our concerns. Are they going to be available at the scale and in the time for our aggressive timeline? We start large. There is no ramp up for us. We start large and we run large from then on. There is no time to gradual increase of the new technology. Introduction of new technology has some risks associated, especially when it's a very early phase of something brand new that just came out. There are some high costs of early adoption. The other consideration for us is interoperability for upgrades and retrofits. We look how to implement the upgrades from Fabric from technology A to technology B as quickly and efficiently as possible. And there are existing fiber infrastructures that we have deployed at scale. And we prefer to augment our fiber plants rather than completely redo them. And we want to prolong their life for multiple generations of networks. Our fiber is single mode, as I mentioned, with LC connectors on the front panel. Another consideration is power. Power is a very valuable resource in the data center, and we would like to give as much of it as possible to our servers, not the network. Each environment by its size has some optimal radix of the switch that allows to cover the available floor plan with the minimum number of network tiers. For us, the magic number is radix 128, 128 ports per switch. That's the best fit for our largest buildings. We achieve radix 128 today by building little networks inside our fabric devices. So for example, in the backpack fabric switch, which is the colored dots on the diagram in the middle tier, there's actually a network running inside consisting of 12 sub-switches. 4 of them aggregate rack switches, 4 of them connect to the spines, and 4 form a little internal spine in the box. Each one is actually associated with a microserver. We run them as individual entities, as individual switches for control plane and management. They talk BGP inside the box. These 12 small radix subsystems were okay at 100 gig. However, at higher speeds and an increasing scale, the efficiency of this setup starts declining. Why? This is essentially 48 individual subswitches serving the pod aggregation function in the pod, 12 per fabric switch, or FSW as we call them. The spine nodes on the upper tier of the network are also actually the same multi-chip systems. And there is optics dependency for each next generation. So when we build out the fabric to the full topological capacity, the next steps may be expand the topology or go to higher speed links. So there is an optics need for every next speed bump. We evaluated a number of alternative topologies inside the box suitable for our application to see if we can reduce the number of subswitches and reduce the power consumption. But we didn't find much improvement. We get some incremental improvements, but not as much as we needed. But our big question is what's next? Let's say we build a network out of multi-chip 400 gig switches with 48 ASICs per pod. That allows us to achieve 1.6 T connectivity per rack. And this is our desired capacity level. But how do we achieve the next 2 to 4x? And we know that we'll need it, and we know that we'll need it not so distant future. Adding more fabric planes on this multi-chip hardware would require too much power for our liking. Increasing link speeds, does this mean that we will need 800 gig or 1.6 T optics in a couple of years? We're just entering the 400 gig territory. So we rethought the whole network topology completely differently. From 4 by 128 port multi-chip 400 gig target, which gives us 1.6 T, we redesigned the network as 16 128 port single chip 100 gig switches. This gives us exactly the same capacity per rack as the 400 gig solution would have gave us, but it uses not 30%, not 25%, it uses 3 times less chips. From 48 FSW chips per pod, we're going down to just 16 by using single chip devices. It's the same ASIC building block as multi-chip candidates, Broadcom Tomahawk 3. It's the same exact rack uplink bandwidth capacity as 4x400, up to 1.6 T per TR. We don't really have 400 gig or like any over 100 gig flows between the servers. And our priority is to increase aggregate capacity, not increase the flow size. We actually prefer smaller flows, but we need lots of them. And this gives us over 3x less chips and control planes in our overall fabric, which improves our efficiency on multiple fronts. It also gives 2 times less power per gigabit than our existing fabrics, and it's built on mature and readily available 100 gig CWDM4 OCP optics. So there is nothing new on the optical front there. Most importantly, it gives us realistic next step scalability. The same advantages that we are enjoying on power in the 100 gig form factor expand to the future generations. And there they become even more optimal, actually. The 200 gig or 400 gig optics can be the realistic way for us to achieve the next 2 to 4x increase in capacity. So we don't need 800 or 1.6 T. And they're already available today. They're early today, but by the time we'll need this next 2 to 4x, they will be mainstream. So let's look on the other aspects of our F16 fabric design. This is our classic fabric. We completely redesigned it. And this is not a simple multiplication by 4. This is a new network by many logical and physical and topological aspects. It supports up to 16 planes, up to 1.6 T capacity per rack for each rack. It's built entirely of single chip Radix 128 building blocks. On fabric switch tier, spine switch tier, it's the same building block applicable throughout. We locked the spine scale at 1.3 to 1 subscription, and we build it as such from beginning. What 1.3 to 1 means that for every 48 downlinks to racks, we have 36 uplinks to spines, not 48. We find that on a pod scale, all servers of a pod almost never talk simultaneously at 100% for an extended period of time. The pod has a diverse set of services. 1.3 to 1 is an optimal maximum subscription level for us. And we also eliminated the edge pods. we replaced edge pods with direct spine connectivity to our next generation large-scale disaggregated FA. Edge pods served us very well. What they did, they abstracted the differences between the fabrics to the aggregation tier. They minimized the radix and normalized the radix on the uplink connectivity. And they also greatly simplified the routing by abstracting all the fabric internals from FA and enjoying the benefits of full mesh FA. We also have 8-plane variant of F16, which we call F16 8P. For this, physical infrastructure, fiber, all long lead time items, we are building as for full F16 from day one. But the number of active planes that start is just 8. This also gives us near terabit capacity per rack. It's 800 gig. If looking at an F16 pod, like this is a 16-plane pod, this is an 8-plane pod, this is a simple reduction of number of planes. The architecture is exactly the same. But it can go back to F16 relatively quickly, to the full 16-plane form factor. It's fully upgradable, it's just a matter of adding devices. We also reimagined our region from the 3-building full mesh connectivity to large FA system and edge pods. We went to direct connectivity from spine to aggregation tier. But how to aggregate these large fabrics? Each one of them can have up to 576 spine switches. No device is simply big enough to aggregate so many ports, even at 100 gig, not even talking about beyond 100 gig. Especially when our goal is to go beyond 3 fabrics. For that, we created HGrid, which is a disaggregated partial mesh aggregation tier. To create HGrid, we connect matching spine switches of all fabrics across all planes into slices, creating a partial connectivity slice by slice. This partial meshing introduces additional routing considerations. We had to completely redesign our routing on the handoff and inside the fabric to go to the partial mesh aggregation. But as I mentioned, our plane design helped us roll it very smoothly. In total, there are 36 slices in the HGrid, essentially spanning all SSW numbers in the spine. An HGrid entity, it's a unit of deployment in HGrid, has downstream units represented on each of the slices and has upstream units, which connect the entity to the outside world, to other regions in our network, to our POPs, internet. So you can pretty much assume that for every row of these orange dots on the diagram, there is also a row of upstream units, and the size for them is variable depending on the connectivity requirements of a particular region. At full scale, F16 Mega Region would look like this. Here we have 6 fabrics, 6 buildings. Each building has full-scale F16 aggregated on the 36-slice HGrid infrastructure. This allowed us to go to petabit level uplink capacity per fabric for each fabric. So from hundreds of Ts, we are going to petabit level capacities. And this is just the uplink. This is evolution of our fabric aggregator design, which we introduced here last year. But it's built on the new building blocks, and I'll talk about that a little bit. The routing is, again, BGP end-to-end from rack in one fabric to rack in another fabric throughout the network. It's pretty hard to contain the routing scale of such a massive region. But we designed our routing implementation for reliability, convergence, and ability to fit into small fib and control plane resources on the nodes. Despite looking this complex and large on these massive diagrams, this network is actually a lot simpler and flatter than our previous fabric design. It's pretty much as flat as it gets for given size of the physical footprint. Looking at our existing fabric, We have all these tiers: fabric switch, spine switch, edge switch, and regional aggregator. But inside each node, there is a small fabric of subswitches. And in total, this gives us 9 distinct chip layers on the network. In comparison, F16 has only 4 chip layers. Yes, it has more parallel elements, but each element is a lot simpler than in the previous Fabric design. So in total, with elimination of edge switch tier, it's over 3 times less chips on the Fabric, and over 2 times less tiers of chips in the Fabric. What this also means, a decrease in host-to-host hops over the network when the hosts communicate together. Like, for example, in the classic Facebook 4-plane Fabric with multi-chip switches, server in one pod talking to server in another pod would take up to 12 network hops between the ASICs of the network. It's actually like 6 to 12. 12 is a worst case, but this worst case is the most abundant because the probability of talking to destination that's located on the same little front panel portion of the small chip is very low in the large distributed system. Most of the paths are worst case paths. In contrast, in F16, it's just 6 hops, always. It's even bigger advantage for talking from rack to rack in different fabrics in the same region. If continuing that path, we go up to FA, we go to the spine of the other fabric, to the pod of the other fabric, into the rack. It's 24 hops worst case. And again, this worst case is the most abundant case. In F16, it's just 8 hops, always. So we get a massive 3x reduction of the number of hops inter-region. What this means the paths are more consistent. There is less queuing points of the path of traffic. All this translates into the improved network performance. As a building block for F16, we created a brand new hardware switch, which we call MiniPack. It's a 128 port by 100 device. It's 2 times smaller in physical size and 2 times smaller in power footprint as our previous FSW platform, Backpack. And it's built around a single chip. MiniPack is applicable as a building block on all tiers of Fabric and H-Grid. It's pretty much used in FSW role, in spine switch role, in both downstream unit and upstream unit of our disaggregated FA. Our rack switches, also our in-house platform, are Wedge 100S. And that's another advantage of F16. Our existing rack switch is compatible with our classic Fabric and with F16. In F16's case, it actually can make racks fully non-blocking. The equivalent of 1.6 T of downstream capacity to servers is complemented by 1.6 T uplink to the network. Another way to visualize applicability of MiniPack on our network is this diagram. MiniPack is used on all these tiers. Every colored dot on this diagram, fabric switch, spine switch, H-grid node, each one of them is a MiniPack. And the rack switch is a Wedge 100. We designed MiniPack from grounds up. It runs FBOSS as our network operating system. But we needed more than one source, given the scale and pace of our deployments. So we teamed up with Arista Networks and created an equivalent of MiniPack together. It's Arista 7368, the same 128 port by 100 4U device with a similar modularity. And it can run either FBOSS operating system or Arista EOS. So both of these, a single chip uniform building blocks in our network, they can be completely interchangeable. The modular PIMs is a distinct option, a distinct property of the MiniPack design, give us interface flexibility. Our networks never stay in the same place. They keep evolving and upgrading. We introduce new technologies, new link speeds, and so on. Having the modules around a single chip allows us to use different optical form factors, different link speeds, and intermix them within the chassis. To summarize, With F16, we are achieving 4x bandwidth at scale without 4x faster links. 8 planes, 16 planes give us new dimension of scaling. We use 100 gig links. We're not forced to go to the higher link speeds immediately, but we achieve the same capacity as what higher link speeds would have given us. We realize power savings both now and, more importantly, in the future iterations. We see clear next steps. We see how we can bring this network 2 times more and 4 times more in capacity. It's actually simpler. The single chip large radix systems improve efficiency greatly. It's flattened, less tiers, less chips, less hops between the servers. We use MiniPack as one flexible building block for all roles in the fabric. And with our disaggregated aggregation, H-grid, we can scale our multi-fabric regions in both bandwidth and size at the same time. There's been a massive development effort between many technical disciplines, and I'm very excited to see it all come together. This was a session about the networking aspects of it, but we have follow-up sessions about hardware details and a deeper dive into the software. You can also see the summary of this information on Facebook engineering blog. Thank you.